Welcome to Tuesday of Globecom 2015 here in San Diego. Again, for those who were not here yesterday, I'd like to welcome you to San Diego. This morning we have an exciting lineup of keynote speakers, beginning with Matt Grob of Qualcomm, Jay Alexander of Keysight, and between the two presentations that the first thing we're going to be giving out our student competition awards. After our morning break, we are actually going to break into having parallel symposium sessions at the technical level, but he'll continue with two more keynotes. Here, Sachin Katti of Stanford and Seiji Onoue of NTT Docomo. Yesterday, I started off giving a little bit of the history of communications and telecommunications in San Diego and talked about Linkabit and the legacy of Linkabit, particularly as it started to form Viasat Technologies, one of the spin-offs from Linkabit. The most successful of the Linkabit, I'll call it spin-offs or derivatives, was Qualcomm, which I believe everybody is aware of. Qualcomm was formed in 1985 by Irwin Jacobs and Andrew Viterbi. This is the 30th year of the company's existence. It has grown to a $25 billion company. I think everyone knows that it is the largest wireless semiconductor chip division, the largest fabless semiconductor company, et cetera, et cetera, et cetera. And of course, probably everybody's aware of the CDMA technology for cellular that it did. Besides being, I think, a pioneering technology, I think it also showed the industry that you could really create and bring very sophisticated telecommunications technology or communications theory and the stuff that we deal with at conferences like this into practice, into commercial communication systems, and stimulated a huge amount of research in the field. And I think we have to add some of that work and the legacy of that. I was actually pleased myself personally to present at Globecom in 1991, essentially our first major public paper on CDMA technology. So I have sort of a strong connection with that. I'd like to turn it over to the first keynote speaker, but let me just give a quick introduction to Matt Grob, who's going to be talking about 4G into 5G here. We've gone from 1G up through 5 here. Qualcomm is the CTO, Matt Grob, I'm sorry, is the CTO of Qualcomm. In this world, he sort of directs the overall direction of our corporate R&D activities as well as the technical direction of the company. Matt joined basically Qualcomm the same year that I gave the presentation at Globecom in 1991 as an engineer. He did a lot of work on a technology that many of you may have heard of called 1X EVDO. That meant for data only or data optimized, which we developed internally at Qualcomm in the sort of late 90s and became standardized in the early 2000s. It became a major early data thing talking about fast feedback mechanisms and things like that, basically sensing channel state and all of that. I'm not going to spend too much more about that, but I think we should welcome Matt here. He holds a MS degree from Stanford University. Matt?
Thanks, Ed.
Thank you.
Good morning. It's great to be here. Thanks, Ed. I want to just add, appreciated the historical comments that Ed made. Ed himself actually has been a major part of Qualcomm since almost the very, very beginning, and has been a mentor for me a lot, since I started in '91. So I'm really grateful to be here, and Ed invited me, I think, a year ago for this event, and I'm looking forward to talk to you about, this is one of my favorite things to talk about, which is where wireless is going. So let's get to that. Let's talk about where we've been and where we're going. So back in '91, when I started, the goal was to improve spectral efficiency because operators were going from analog to digital, and the usage was coming up, and there wasn't going to be enough spectrum, and there was kind of a concern about that, so the industry needed more capacity for voice. And as time went on, Ed mentioned EVDO. We originally called that DO for data only, and then we called it, because we were only going to use it for data, then we called it DO for data optimized, and then we started to do VoIP on it, so we called it data optional. And eventually, data traffic started to surpass voice traffic, and around 2002, mobile started to surpass fixed in terms of the number of connections. So there were now more connections for mobile devices than there were for fixed. And then as we started to connect the internet to mobile devices, and we had the explosion of mobile internet, things like EVDO and HSP and others bringing higher speeds to that, we reached the point where now mobile computing and mobile connections for internet surpass those for wireline and fixed. And around that time, voice became, just percentage points of the total amount of traffic. And that's where we are today. However, it feels the same. We still have usage going up, spectrum being, we need to use it as efficiently as possible. We're going to go to more and more extreme measures to get the last drop of efficiency out of it. The operators need these solutions. It feels like the same kind of situation as at the beginning, except now it's not just for voice. Now the next step is, and this is what I'm going to spend my talk about, is where we're going. It's phones, of course, but it's going to be so many more applications and use cases and interesting requirements that we have to do a lot of work to make all this happen. Okay, so think of it as a new connectivity paradigm that we'll need for 5G. In the past, it was human communication. You were talking people to people, like a voice call or a text message, or you're talking a person to a machine, like you going to Amazon, it's a server and a person. But we need to set up the situation for all kinds of machines talking to each other and different paradigms of communication, anything, anywhere. We need to move beyond just best effort data services, which is what we have mostly today. Even though QoS has been defined for many years, most of the services are generally best effort internet services, or most of the traffic, into different kinds of paradigms that include things like proximate discovery, multicast, peer-to-peer, and then, of course, many different flavors of QoS, and we're going to talk about that. We want to be able to converge different kinds of networks that have different spectrum regulatory paradigms, licensed and unlicensed, and different scale, high-speed devices with multimedia, all the way down to sensors and IoT devices. Okay, so a question that I get asked all the time is, what is the vision for 5G? And I want to answer that as best I can in this talk. Now, it's not something you can just say like a sentence that says, we're going to connect everything super fast. It's more than that. It's more rich. So we can look at different elements of what we expect the future to bring. We want scalable. We want to have everything from very high speed 4K video and beyond, and I'll explain to you why it needs to be beyond 4K, significantly so actually, all the way down to tiny devices in enormous numbers, maybe numbers like tens of billions or even a trillion, and have that be serviced from a common network. We want to unify. We want to unify different spectrum regulatory paradigms. We want to unify different bands and be able to have devices that go all the way from sub-gigahertz to millimeter wave, and different throughput classes like I mentioned. And the reason we want to do all this is we want to enable new kinds of services that the operators can offer. Right now, for example, if you wanted to do control of an autonomous vehicle, or if you wanted to do a medical procedure, you can't do it on cellular today without adding additional reliability or maybe some additional security. You have to take some measures in order to use it. And when I say, for example, a medical procedure, I'm talking about a case where you have It's beyond just like a fitness band. Those are fine, that's all good. But we're talking about where there's a physician and a patient on the opposite side of a radio link doing a procedure. What kind of requirements do you need from your cellular network to do that? So we want 5G to bring in higher speeds, higher peak rates. Of course, everyone always talks about that, and we're going to deliver that. But it also needs to enable new services. It needs to have different classes of reliability, different classes of latency, and be able to span all these different kinds of paradigms in a unified manner. And doing that will give us the ability to handle some interesting use cases. So here's a chart of all these, and I'm actually going to take a minute to go through some of them in a little bit more detail. On the bottom left there, you see one that says demanding conditions. Okay, what do we mean by demanding conditions? There's a picture of a sports venue. Now imagine what we're facing now versus, say 20 years ago. If you have an outdoor sports venue, let's say a big football stadium or maybe a NASCAR track, let's say there's 100,000 people in there. What did you do before? Well, some fraction of them, maybe a third, would have cell phones. And they wanted to do voice and text, and they would make a call every now and then. You could compute the Erlangs and the blocking and decide how many channels you needed and how much backhaul you needed. And you'd end up with a number, something like 10 megabits per second of backhaul would be enough to service every voice and text user in that stadium. 10 megabits per second. Can do 100,000 users under those conditions. Today, every single user wants 10 megabits per second. They're not even happy with that. They want 100 megabits per second or more, every single one of them. At something like the Super Bowl, the smartphone penetration is 100%, if not 120%. So that's orders of magnitude more than it was. And it's in both directions, by the way, because people are now generating content like never before, sharing their experiences, sending videos. Even phones from a year or two ago could author 4K video, and they want to send it on the uplink. And you have events at these venues that correlate, maybe a halftime or a timeout, and that's when everyone goes to their phone. It's incredibly important to get this right. If you don't have good services at these places, people won't go anymore. They need that. So that is what we call a demanding condition. And that puts requirements on the network to scale to unprecedented levels of density. We're doing work right now where we're deploying small cells on a density equivalent to 30,000 per square kilometer. So compare that to the past where a sector might cover a square kilometer, and you start to realize you no longer only want coverage, you want to be able to reuse and have incredible density, along, of course, with ubiquitous coverage everywhere in a metropolitan area. And that's when we talk about the 1000x, and that's why we have to push 5G to be able to operate in these kinds of regimes. The next one is extreme mobile broadband. Of course, faster, wider, higher peak rates. That's definitely a part of this. As we define wider bands, instead of doing a large number of carrier aggregation, we can have a fundamentally wider band with 5G. That makes a simpler receiver, a simpler modem, lower costs, and allows us to scale. New form factors. Okay, so you see the picture there of a wearable device. Well, that's certainly something we're working on. But let's ask, what is going to be the form factor 10 years from now? I'm going to talk in a minute about the schedule of 5G. Realize that for 4G, which has just been a tremendous success and is hitting stride right now, it was really defined, the physical layer design came before, say, the iPhone, a couple years before even. What is going to be the form factor when 5G hits stride? Is it still going to be these rectangles that we walk around and go like this? Well, maybe, maybe not. A quick anecdote on that I like to tell. We visited Twitter recently, and they showed a picture of a whole bunch of people standing by a train station, and every single person there was looking at their phone, except one person was looking up, and they were like, what's that guy looking at? But everyone was looking at their phone. And then they showed a photograph, and by the way, Twitter feels like they get blamed for this. People say, you're the ones who caused this. They showed a photograph of people on a train from the 1930s, on a trolley train. What was every single person doing? They were all looking at a newspaper. It was the same as today. They were looking at text and pictures of the news of the day. The difference was it was updated once a day. Today it's updated once a second. What's it going to be 10 years from now when people are walking down the street or at a train station? Well, maybe it's still going to be the rectangles. That's certainly going to be part of it. But more likely, it's going to evolve to new types of form factors, including head-mounted displays and digital eyewear. And if you've ever tried one of those, anyone here tried Oculus or any of those, or Google Cardboard, you quickly realize that you need to have a heck of a display. Like, let's say these screens here are 4K screens. But look how much of the field of view they occupy when you're sitting there, only a small fraction. If you want your entire field of view to be of that quality, you need to go well beyond 4K. So you can envision the future where we're going to have dense users moving media in both directions with very high resolution. We're going to have to mix high and low latency traffic. That's what we're talking about with new form factors. Okay, smart cities, homes, we've all used ever increasing levels of home automation, Nest, and better access points with Wi-Fi, and connect to your car, and all these things. There's all kinds of industrial use cases, and so that's going to be a big part of it, and that also gets back to the reliability and security that we'll talk about in a minute. Autonomous vehicles. Guess what? Autonomous vehicles are here. They're no longer in the future. For many years, you'd read about, there's going to be self-driving cars someday. And then you'd see prototypes, and you'd see the Google car, and you might have met someone, a couple of us that got to ride in that thing. Well, guess what? Now today, I actually have some friends at work, at the office, who have purchased the Tesla car, and they've downloaded the autopilot, and they go out into the highway, and they turn it on, they take their hands off the wheel, and they change lanes that way, and it's not a prototype. That moment is now in the past. It's no longer in the future. But to really take advantage of it and have large numbers of vehicles being able to do this, being able to map locations and to be safe and to reduce accidents, we're going to need networks that are up to the task. That relates to critical infrastructure. Again, mission critical. We talked about medical procedures. We need a network that can provide, upon request, a highly reliable service. And then remote control and process automation. There's a picture of a drone there. That's something that we're excited about. A lot of people are doing interesting things. We've started to do vertical coverage measurements of our networks now to see what happens when you're a couple hundred feet above, to investigate the option of the potential of commercial use cases of these exciting new devices. Multiple of the operators are interested to be the control system in those cases. So all this together is the vision for 5G. It's not just higher peak rates, although that's part of it. It's this whole picture. Okay, so after the vision, the second question that I get asked more than anything is, okay, when are we going to have all this stuff? What's the schedule? I keep hearing this, I keep hearing that. Well, this is our view of it, okay? We've obviously had the beginning of the process now in 3GPP, the process to generate study items. That's taking place. There was a workshop a month or two ago that started that process. So our view of the schedule, which is I think the mainstream view here, is that there'll be release 15 derived 5G work items that are developed between 2017 and 2018. And that will lead to service or launch of so-called phase 1 of 5G around 2020 timeframe. When we say phase 1, that means it still has elements of 4G LTE in it. It can use 4G LTE as a control plane, and so it's kind of a multi-mode step. A lot of the work in that early phase is likely to be at sub 6 gigahertz. Then comes the release 16 family that will be developed in the 2018-19 timeframe, and that will be launched 2021 timeframe. That will be including the whole thing with the millimeter wave, the modes that are 5G only, and that that's really the ultimate 5G there. After that, it keeps going. We've called it release 17 plus. I guess at some point there'll be 6G, but I don't want to say that yet. Meanwhile, 4G is going to continue to evolve. I think of it like in aircraft terms, 4G is like the 737. It's a workhorse. It's deployed by many operators. It's very solid, dependable, and yet it's still being improved with new engines, new wings, and the 5G is like the 787, which is a little bit more like a start from scratch, but you can get even higher performance. Now, people then say, well, what about 2018, millimeter wave? What about, I hear these stories in the news about the operators wanting to go faster. Well, there are cases that we can go a little faster for some of the configurations and do some market trials and some other activities, but we really believe that the mainstream official standards-based effort is more or less along these timelines. And we want it to be this way. We want 5G to be a significant step forward, and so to have the time developed to make that happen. Okay, now let's talk a little bit about the air interface. We call it a unified air interface because we want it to span different regulatory paradigms, like licensed spectrum, like we have today, unlicensed spectrum, and things in between, like semi-licensed or secondary use. For example, in the US, we have 3.5 gigahertz. There's a primary incumbent user, which is the government. They need to use it in certain situations. Secondary user, there's even a third tier. And we want 5G to be able to operate under all those paradigms. We also want to facilitate what we call neutral host, which means in the past, cellular has been associated one-to-one. There's been one channel, one physical channel with one system or one operator, whereas on the unlicensed paradigm, which wireless LAN, which grew out of wired LAN, has always had the media sharing notion where you can have multiple operators sharing that channel. That is why it's very popular in places like this where you can welcome subscribers from any operator network and use the unlicensed band. We want to give cellular that same capability. Of course, we also want to unify across the bands themselves, from sub-gigahertz to a couple of gigahertz traditional, all the way to millimeter wave, and it's going to be very important to be able to move efficiently between them, and I'm going to show you some test results in a minute. Both FDD, TDD, half duplex, and actually there's some exciting startups working on full duplex, or I guess you could almost call it non-duplex, and that's pretty interesting, could become part of this as well. And different topologies. Since the beginning of cellular, it's phone and base station, but we want to have peer-to-peer and mesh and those other topologies. Now, we've added some of those to 4G, but they were added after the fact. We can design in from the beginning on 5G. And then I mentioned the different types of services, from high speed to low speed, multiplexing different types of traffic with reliability, different classes of user mobility. If you have a thermometer in your house, you don't want to bear the core network expense of supporting that as a fully mobile device. Yeah, maybe it still moves. Maybe you take it out of your house and move it to some other place, but it's not going to hand off like a voice phone would. In return, you can have lower network costs, which is what's necessary for those kinds of devices. The annual network cost needs to be a small number of dollars so we can have trillions of them. And